right, this is going to be objective 29. We are going to graph exponential functions, and we're also going to solve exponential equations. Graphing exponential functions you did in Algebra 2, okay? We looked at what an exponential function looks like. We looked at the domain. We looked at the range. I'm just going to kind of refresh your memory with that, and then we're going to head on into the new part. We're going to actually solve exponential equations today. All right, so an exponential function is a function where the base is a constant and the exponent is a variable. If you had me in Algebra 2, I always said when x is the exponent, it's exponential. Does that make sense? When x is the exponent, your function is exponential. Okay? The parent function is written in the form y equals b to the x. And it can either be a growth or it can be a decay. So it can look something like this, or it can look something like this. Okay? This is not, it does not make an L shape. It does flatten out horizontally. How do we know? What do we say when it flattens out horizontally? It's going to create a horizontal asymptote. Okay? We talk logarithmic and we talk exponential. Logarithmic and exponential are inverses of each other. Okay? And one of them has a vertical asymptote. One of them has a horizontal asymptote. Okay? I always use the saying, a log is a tree and a tree goes up and down. So a log has what kind of asymptote? A vertical asymptote. Therefore, an exponential would have a horizontal asymptote. For example, both of these flatten out, meaning they are approaching this line right here. Okay? An asymptote means the function is approaching it, meaning it's getting really, really close to it, but it doesn't ever quite touch it, and that's your asymptote. So this would have an asymptote, a horizontal asymptote at y equals 0. Okay? That would be your HA, or your horizontal asymptote. Okay? Yes, several of you did a PBA for me. I asked you a question. I said, actually, maybe I should try it out on someone I didn't teach Algebra 2 to. Alessandra, you want to be my guinea pig today? Okay, here we go. So, I want to hire you for the summer to babysit my kids. Okay? I'm going to pay you a penny a day. And I'm going to double it each day. Would you come and work for me for 1 month? Let's think about this. So day 1, you get a penny. Day 2, if I double it, you would get 2 pennies. Day 3, you would get 4 pennies. Day 4, you would get 8 pennies. Day 5, you would get 16 pennies. Let's go 1 full week. Day 6, you would get 32 pennies, 32 whole cents for babysitting my children. Whew. Okay. And day 7, you would get 64 pennies, right? So all in 1 week, how much have you made in 1 week? Like, well, if you add it all together, you would get like $2 and something. Okay. So my question is, and there's no wrong answer here because generally my students all answer a certain way every time I ask this, but would you work for me for a month? Yes. Why are they saying yes? Like, so we did a PBA in Algebra 2. We actually graphed it out, and I asked the question, would you work for me for a full month? At the end of 30, like, yes, it starts out really slow. Check this out. It starts out really slow, so after like the first week or so, you're still like at the bottom. But then all of a sudden, when it starts to double, it starts to skyrocket. And by the end, on day 30, it's like over $1 million. I want to say it's like $5 million, something. And when you add it all together, add day 1 to day 30, it ends up being like $10 million. It's like an insane amount. And No one ever believes that until you plotted it out. So yes, that is, it starts out slow, but then it all of a sudden, and it skyrockets. Okay, it all of a sudden skyrockets. You can have a decay the same way. Okay, I always talk about like when a new restaurant comes into town, like when what's the place in Patrick Springs that opened up but then closed? Yeah. Okay, so when it first opened, like everybody was so excited. It was like waiting lines and it was like packed. And then all of the sudden, what happened? Well, but people got used to it. Anytime a store opens, it's like a lot of excitement in the beginning, but then it will start to decay slightly. And then it gets to a certain point and it just levels off. And that's the same amount of, you end up making the same amount of money. So, you know, decay works the same way. Decay works the same way. Okay? All right. So, as we get into solving exponential equations, I want to review our laws of exponents. So this is what you learned in Algebra 2. We've talked several of them this year, but I want to make sure you understand all of them. So you know that if you have 5 to the second times 5 to the third, if they have matching bases, this is your first law. When you multiply powers, you add the exponents, so this could become 5 to the 5th power. The base will stay the same. Base stays the same? Good. All right, number 2, you know when you are dividing 6 to the 5th power divided by 6 to the 2nd power. When you multiply powers, you add the exponents. When you divide powers, you subtract. And that could give you 6 to the 3rd. Okay? Law number 3. 5 to the 0 power, anything to the 0 power is equal to 1. Anything to the 0 power is equal to 1. Okay? That is based on, and I'll just share with you, just remind you, that rule right there is based on your powers of 10. Like we know 10 to the 4th is equal to a 1 with, how many zeros? 4 zeros. 10,000. We know 10 to the 3rd is a 1 with 3 zeros. We know 10 to the 2nd is equal to 1 with 2 zeros. We know 10 to the 1st is a 1 with 1 zero. Anything to the 1st power is itself. We know 10 to the 0 power is equal to 1 with 0 zeros. Anything, and it doesn't matter if it's 10. Anything to the 0 power is equal to 1. Okay, 5 to the 0 power, x to the 0 power, 8 to the 0 power is equal to 1. Okay, but that's just kind of where it's based off of, is your powers of 10. All right. 2 more rules. We know, 4th rule, we know if I have 2 to the 3rd power raised to the 4th power. If I have a power raised to a power, that is equal to, what do you do to the exponents? You multiply them. 2 to the 12th power. Okay, any questions about that? And the 5th and final one, and this is one of the most important ones that students forget about all the time. If you have 6 to the negative 2 power, most people think that's equal to negative 36. Okay, that does not mean I square it and make it negative. Okay, you cannot multiply something a negative amount of times. Do you understand that? Like when the exponent says I'm going to multiply 7 times 7 times 7 times 7 times 7. The exponent, if it's an exponent of 3, it would be 7 times 7 times 7, 3 times. Okay, you can't multiply 6 a negative amount of times. So how do we fix it? You make it a fraction, and we move it through what I call the magic mirror, or you can just move it through the denominator, and this will become 6 to the 2nd. What's up top? A 1, and then you can make that 1 over 36. Okay, please listen. Any questions about that? Okay, any questions about how many remember these rules? Yes? Make sure you have them. Make sure you remember them. You're going to be using them. Okay? All right. It's important. What we're going to do today is we're going to solve exponential equations without our calculator. So you've got to know your perfect squares and your perfect cubes. Okay? And so I'm going to give them to you so that you know, so that you have a list of them. So let's start with perfect squares. All right, here we go. Ready? All the way to 20. 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, 7 squared, 8 squared, 9 squared, 10 squared, 11 squared, 12 squared, 13, 14 squared. You know how I remember those two? They're just flipped. Okay? 15 squared, 16 squared. Very good. 17, 289, 18, 324, good. 19, 361, and 20, 400. Okay? I also think you should know your perfect cubes. You need to recognize your cubes as well. Okay, so anytime I see today, like you've got to know these numbers because we're not going to use our calculator. You know, if I see 289, I automatically think, oh, that's 17 to the second power. That's 17 squared. You need to be able to relate those numbers and to what their squares are. Okay? Perfect cubes. 1 to the third power. 2 to the third power. 3 to the third power. 4 to the third power. 5. 6 to the third power. 216. 7. 343. 8 is 512. 8 to the third power. 9 to the third power is 729, and 10 to the third power is 1,000. Okay? I'm also going to, so you need to be able to recognize those. Like generally, I'm going to give you, I don't want to say baby problems today, but smaller problems. So it'll be something squared, and it'll be one of these numbers, or it'll be something cubed and one of these numbers. Or they'll give you a base of 2 or a base of 3. So I'm going to go ahead and give you like your 2's, like with a base of 2, 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth. So you'll have those because that will help you as well. So I'm going to give that to you. So we know, excuse me, we know 2 to the 0 is equal to 1. 2 to the first is equal to 2. 2 to the second is equal to 4. 2 to the third, 8. 2 to the fourth. What's 2 to the fourth power? 16. You're going to want this list because you're going to want to refer, because I'm going to say, all right, guys, what's 16? And y'all are going to say it's the same thing as 2 to the fourth power because you're going to have to make them have matching bases. Okay? 2 to the fifth is 32. 2 to the sixth is 64. 2 to the seventh is 128. 2 to the eighth, that's probably as high as we need to go, is 256. I'm going to stop right there. And then I'm going to give you your 3's, okay, a couple of them. Because you're going to use, like I see this one used a whole lot, and I see that one used a whole lot. I also see that used a whole lot. So you need to make sure you know, you got to be able to take 32. When I see 32, I think, oh, that can be written as 2 to the fifth. Okay, I'm not going to give you 2 to the 5th and say, what is it? I'm going to give you the number 32, and you're going to have to write it as an exponent. Okay, does that make sense? Like if I give you the number 64, how could you write it? You could say 2 to the 6. What's another way? You could say 8 squared. What's another way? 4 cubed. It depends on, do I want to make it have a base of 2, 4, or 8? But you're going to have to make it have matching bases, so you kind of need to know these numbers. So 3 to the 0 is equal to, anything to the 0? 1. Okay, 4, not 4 to the 0. 3 to the first is 3. 3 to the second is 9. 3 to the third is 27. 3 to the fourth is 81. 3 to the fifth is 243. I think that's probably as high as you need to go. Okay, but I just wanted you to kind of have those when we get into the equations part to refer back to. Okay, your perfect squares, your perfect cubes, your powers of 2, your powers of 3. It wouldn't hurt to have your powers of 4 on there, but okay. So we're going to start here first, and we're going to graph, and then we're going to state the domain and the range. Okay? So you're going to use your calculator. Well, we're going to solve without the calculator. You're going to graph with the calculator. Okay, we're going to use our calculator, and we're going to put in 3, y equals 3 raised to the x power. Now, the easiest way for you to graph this is to go to your table and just get you some good points to plot. Okay, so I would go second table, and somebody give me some good points to plot. 0, 1, so I'm going to go 0, up 1. What else? 1, 3, and you can just sketch this on your paper. It'll be all right. I'll actually give you graph paper in just a little bit. 2, 9, so I'm going to put that up here. What about, you probably need some negatives too. So what's negative? Because if all I did was this, what does it kind of look like? It kind of looks like half of a parabola maybe. Like it looks like half of a U. So you need some negative numbers too. Can somebody give me, and you're going to have to graph decimals. So -1 what? 0.3, where's 0.3? Like in between 0 and halfway up. Okay. Then -2.1. Then -3. And so you can see that what happens is it gets closer and closer to 0. If you keep going, it actually does what? It gives you an E message. What did I tell you that E message meant? It means 0, but does it at your, so your calculator tells you that it gets to that number. Does it actually hit that number? No, the calculator rounds it. It gets so close that it just like puts it at 0, but I need you to understand it does have a horizontal asymptote. It doesn't actually get to 0. Okay? So, all we're going to do is we're going to state our domain and our range. Anybody want to take a stab at remembering from Algebra 2, domain and range? Well, range is highest minus lowest, but that's when you're talking like box and whiskers and data. When you're talking a coordinate plane, domain are your x's and range are your y's. Okay? Domain, x's run in which direction? Left to right, and range runs up and down. So here we go. Ready? You tell me this. How far to the left does that line go? Forever. How far to the right? And everybody says, Miss Corns, it ain't going to the right. It's going up. But he is going like in a northeast direction. He's not going straight up. So it's not an L. Does that make sense? It's kind of, this line right here is going in a, it's going up and right at the same time. So my question is, how far to the right? Forever. So forever left, forever right. What would the domain be? All real numbers. Very good. Okay, and that is the symbol for all real numbers. Looks like two lines and then make a capital R. Okay. Or you can just write all real numbers. Okay. All right. Let's talk about range. Range goes up and down. How far up does he go? How far down does he go? Does he actually touch 0? But he's heading towards 0. Okay. So you have to make a statement to that stopping point. So we would say our range is all y's such that y is what to 0? Where is your function? Is it? It's on top of it, right? So it's going to say y is greater than 0. Why not equal? Because it doesn't touch it. 0 is an asymptote. Any questions on that? Okay. All right. So let's look at this one. So I want you to put it in your calculator. Make sure after you do 2 to the x, make sure you use your arrow and get back down, because otherwise it will put it up with the exponent. Does that make sense? So make sure you use your arrow and get back down and do 2 to the x plus 1. All right, so give me some good points for this. All right, -1 and 1.5. Okay, what else? 0, 2, 1, 3, 2, 5, 3, 9 is going to be up here. And then -2, it's getting awfully close to what? It's getting awfully close to 1. Anybody tell me why? Like, I can look at it and know that my horizontal asymptote's at 1. Anybody know? Like, even before I graph. Because it's +1. What does a +1 on the end of it do? It shifts the whole thing up 1. I think last semester, what did we say? X out, log in. So X out, if it's on the outside, it's going to shift it up 1. All right. So tell me about your domain. How far left? Everybody agree? Negative infinity? How far to the right? Positive infinity. So what's my domain? All real numbers. What do you know about exponential functions and domain? It's always going to be all reals. Okay, the domain is. What do you think about logarithmic? If logarithmic are the opposite of that, the range will always be all reals. Okay, but for today, for exponential, the domain's going to always be all reals. All right, so range goes up and down. How far up? How far down? It goes to 1. Does it ever touch 1? So make a statement to that 1. All y's. Ugh, can't draw my thing. All y's such that y is greater than 1. Okay, any questions about that? All right. Do I need to do any more graphing with domain and range? Everybody okay with those? Then I'm going to skip the next example, and I'm going to head straight into, so we'll just make this 3, and I'm going to head straight into solving. I want to get into the new stuff, because this is fun. All right. There is a property that says when your bases match, you can, and you're trying to solve for the exponent, the bases can cancel out. Does that make sense? And you can set 2x minus 5 equal to x plus 3. Okay, so that's kind of the game today. The name of the game is to make our bases match. So then you can just set exponent equal to exponent and solve for x. Okay, so what would I do to solve? Very good. So I'm going to move the x over. So 2x minus x is x. And then what? Move your 5 over, so x is equal to 8. Okay? Why don't you try it and plug it in and see if it works? Put in 3 raised to the 2 times 8 minus 5, and then put in 3 to the 8 plus 3. So what is 2 times 8? This would be 16 minus 5. So this would be 3 to the what power? 16 minus 5, if I worked this out, is 11, right? 16 minus 5 is 11, okay, and what's 8 plus 3? So will they be equal? Yeah, and 3 to the 11th is going to be an insane number, right? 3 to the 11th, I mean, you may even in your calculator get an error with it because it's 3 times 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 3, 11 times. It's going to be an insane number. But if you plug it back in and work it this way, you can see that they will work. Oh, did it work? Okay, good deal. It's still going to be a big number. Sometimes, like, what if it was like 3 to the 33rd? Does that make sense? Then it would, sometimes it can give you an error. All right, so this will be example 4. So what's wrong with this problem? Or my question is can I immediately set 2x plus 3 equal to x minus 1? No. So we need to make our bases match. Okay, and generally you're going to take the bigger one and try to make it match the smaller one. So my question is there a way that I can take 27, you can make 27 equal to 3 to the 3rd power, and then you have your x minus 1. So now your bases match, so what can you set equal to each other? 2x plus 3 would be equal to you would need 3 times the quantity of x minus 1. So take a minute and solve that. You could, but just be careful. Don't just say 3x minus 1. It'd have to be 3 times x and then 3 times negative 1. All right, so take a minute and solve that. All right, so 2x plus 3 equals 3x minus 3. I'm going to move my 2x over here and subtract 2x. So x minus 3 is equal to 3. And when I move this over here and add 3, x is equal to 6. Any questions about that? And you can plug back in and check it and see if it does work. Very good. You ready to try one on your own? Okay. Yes, we can. Let me give you a helpful hint before I give you a second to think about it. What has to happen? We have to make matching bases. That's the key. You've got to make matching bases. Well, 3, you can't really change much of 3, can you? So my question is I want you to think about it. Don't say it out loud. I'll just give you a second to think. How can we take 1 divided by 9 and make it have a base of 3? Okay? 1 over 9 and make it have a base of 3. What can we change 1 over 9 to? Very good. 3 to the negative 2. If you're missing this and you're like, I don't know how you got that, we know 9 can become 3 squared, correct? But then I've got to get it back up here so that it's a base without a fraction. Does that make sense? We can't set them equal to each other if they're in fraction form. So if I move this up, it will become 3 to the negative 2. Does everybody agree that 3 to the negative 2 is the same thing as 1 over 9? So this is going to become 3 to the 2x minus 1 equals 3 to the negative 2. You can cancel those out, and you can set 2x minus 1 equal to negative 2. And then when you move this over and add 1, you've got 2x is equal to negative 1. And then when you divide by 2, x is equal to negative 1/2. Any questions about how we did that with negative exponents? This right here? This is 3 squared. I just drew an arrow up because I'm going to move him up through the fraction bar, and when he comes up, he's going to change to a negative. Anytime you change your base and exponent through the fraction bar, it will change signs. Okay? All right, so you try this one on your own. See if you can get it. So we can make 4 2 to the second times x plus 5. And we can make 8 2 to the third times 2x plus 1. And you can cancel out the bases. And 2 times x plus 5 is equal to 3 times 2x plus 1. Okay, when I distribute 2x plus 10 is equal to 6x plus 3. I'm going to move the 2x over here and subtract 2x. So 10 is equal to 4x plus 3. And then I'm going to move the 3 over here and subtract 3. So 7 is equal to 4x. And we divide by 4, so x is equal to 7 over 4. Did anybody else get that? Yes? Did I make any mistakes? It's Monday. I definitely can make mistakes on Mondays. All right. One last one. Is this easy, hard? Pretty easy? Okay. There's not much more to this, okay, as far as today goes. All right, last one. This will be example 7. There's nothing more for today other than this. All right, so we can change 16 to what? 2 to the 4th power times x plus 1. Let me get my board to write. And you can change 32 to 2 to the 5th, but then it's got to move through the fraction bar, so it's going to become 2 to the negative 5th. Okay? Anytime you see a fraction today, what is that going to imply to you? A negative exponent. Does that make sense? A negative exponent. Okay? So then we can say 4 times x plus 1 is equal to negative 5. And then 4x plus 4 is equal to negative 5. And I move this over and subtract 4. 4x is equal to negative 9. And we divide by 4. X is equal to negative 9/4. Did y'all check it? Did y'all check it to make sure it worked? I might would. I don't know. Check it. See if it works. Put in 16 raised to the negative 9/4 plus 1 and see if that gives you 1 over 32. Yes? Okay. So it does work. Always check your equations just to make sure that you did it correctly.